So now that you've seen some of these equations that actually relate energy and frequency and wavelength and frequency, let's go ahead and practice using some of them. So here's an example problem, something you might see on an exam or your homework. So a helium neon laser, a HENI, has a wavelength of 633 nanometers. That's the little nm. What is the energy of a single photon from that laser? So far we have had these equations here. Energy is equal to hv. Notice it's asking for energy, so we know we're going to be needing this equation right here. We also have C equals lambda V. Okay, both of these equations you're going to have to memorize and know how to use for the next exam. So what you have to do is essentially rearrange and combine these two equations. So first off, we are given a wavelength, so we'll need to rearrange this equation for frequency and plug that into this equation up here, okay, because we're given a wavelength. So first off, C equals lambda V becomes, for solving for frequency, C over lambda equals nu, right? Because we don't have nu, but C is a speed of light, so it's a constant, and this is the wavelength, which is given in the problem. All right. So now we'll plug this equation up right into here, so this becomes E equals hc over lambda. And this is actually a form of this equation that you'll use fairly frequently. So you might want to just memorize this equation too, or remember how to derive this equation, whichever one's easiest for you. So now we can actually start plugging in numbers. We have everything we need. So the energy is equal to Planck's constant, which is actually not on this sheet. This is actually a conversion sheet, but it's 6.626 times 10 to the negative 34. And that would be joules times seconds. Now joules is your energy unit here, and of course seconds is your time unit. Okay, so then we put in the speed of light, which to 3 sig figs is 3.00 times 10 to the 8th meters per second. Okay, so meters over seconds. And then on the bottom we need the wavelength, which is 633 nanometers. But nanometers, if we look at here, we'll end up trying to cancel nanometers with meters up here, so we need to convert this into meters. Remember the conversion between nano and the regular unit. So 1 nanometer is 1 times 10 to the negative 9 meters. All right, so we bring up our calculator here, and we start plugging in numbers. Okay, so now that we have the calculator up, we do 6.626 exponent negative 34 times 3 exponent 8 divided by this on the bottom, 633, and then divided by 1 exponent negative 9. So negative 9. Alright, so our energy here is 3.14 times 10 to the negative 19th joules. So energy equals 3.14 times 10 to the negative 19th joules. Just one more type, okay? A diode laser, wavelength of 785 nanometers, is turned on for a period of 1 minute. So 1 minute is 60 seconds, right? During that time, it emits a signal with a total energy of 31.0 joules. How many photons have been emitted? All right, so there's a few things that we're going to need to do here. We're going to have to figure out what the energy of a photon is at 785 nanometers. So again, using that, energy is equal to hc over lambda. Remember that derived equation from our last example. So that'll give us the energy for a single photon. Okay. And then we are going to have to divide that energy, the energy for the single photon, by the actual energy given here to see how many photons have been emitted. Alright, so anyway, here we go. So again, plugging in the Planck's constant, 6.626 times 10 to the negative 34 times the and that's joules seconds times the speed of light, 3.00 times 10 to the 8th. It's not letting me write all the way over here, so to the 8th. Yeah, it's erasing it, but 10 to the 8th meters per second. Okay, so that's another thing here. And then on the bottom, we have the 785 nanometers. Remember, we got to convert it into, so this is nanometers. We got to actually convert, so 1 times 10 to the negative 9 meters over 1 nanometer. The nanometers cancel. Look what happens to the units here. We got meters that'll cancel here with meters. We got joules that'll cancel here. Or seconds that'll cancel here with inverse seconds, or 1 over seconds. Okay, so the meters are canceling with the meters, the nanometers are canceling with the nanometers, and the seconds are canceling with the seconds. We'll get it in joules. Plug it into our calculator. And again, because of order of operations, we don't actually have to do what's in the parentheses here first. We can just plug it into the calculator it is. So 6.626, and then exponent here. And then we have negative 34, okay, times 3. Remember, it's exponent 3 to the 8th. Because it's 3.00 times 10 to the 8th. Remember, it kept erasing it. So divided by 785, divided by 1, exponent negative 9. And we get this. So this is the energy per photon. So it's 2.53. Let me write this down. 2.53 times 10 to the negative 19 joules per photon. Okay, this is how many photons have emitted. If we have 31.0 joules divided by 2.53 times 10 to the negative 19 joules per photon, and I'm just going to put photon here. Well, remember, if something's in the bottom, it's if it's divided by that, it's photons to the negative 1. Well, the photons would just go up here into the numerator. And so, calculator back out, we have 31 divided by 2.53 exponent to the negative 19. So it ends up being a huge number. Let's see here, to 3 sig figs. So it's 1.22 times 10 to the 3, 6, 8, 3, 6, 9, 12, 15, 18, 19, 20. So 1.22 times 10 to the 20th photons. And that would be our answer there. And so these are how to actually work questions with energy, frequencies, and photons.